welcome back to Luke's Math. Alright, today we'll begin by looking at the exercise I assigned on Friday, going over the solution to it. So there were three different parts to this problem. We're looking at different probabilities, so we know there are only three possible events to occur within the experiment. It's either A, B, or C. So that tells us these events are mutually exclusive because we know only one will occur, and we know we're guaranteed to get one. So they have to equal the three events, the union of them have to be equal to the sample space. So using that information, we'll start by solving A. A tells us that all three are equal. Well, we know that all three events have to be the sample space. So we know that when we add the three, and we're going to use this fact for all three, so maybe rather than writing it down over and over again, I'll just stress the importance. We have that the probability of A plus the probability of B plus the probability of C have to be equal to 1. And so in A, if they're all equal to each other, well then we're going to have 3 of the probability of A. Because the probability of B is equal to the probability of A, and so on. So the probability of A is equal to 1, which is equal to the probability of B and is equal to the probability of C. Okay, let's move on to B. Same fact, we're using that they all sum to 1. But here we have that C is equal to 0.5 and the probability of... So let's start by writing out that they have to all sum to 1. I feel like I'm getting better at writing. Okay. And now what we can do is we can substitute in the stuff that we have. So the probability of A plus another probability of A, since the B is just equal to A, plus we know the probability of C is equal to exactly 1/2, so that's got to sum to 1. And so when you do the math, you get that the probability of A is equal to 1/4, which is the same as B, and the probability of C, well, we already knew that was 1/2, so we're done. Okay, last one, part C. This one has a weird relation, but start by doing the same thing. And then we'll know, well, we're going to try to write everything in terms of A. So we'll have the probability of A. We know that B, if it's 2 times B is equal to A, then B is equal to 1/2 of A. So we can say, I didn't mean to write an equal sign there, but we can say that this is plus 1/2 times the probability of A. Same thing for C, except there's a 3 out front, so it'll be 1/3 the probability of A is equal to 1. So when you add up all those together, you get that 11/6 times the probability of A is equal to 1. So the probability of A has to be equal to 6/11. And then we'll use the facts that we just talked about to derive the other ones. So this one is half of that, so it'll be 3/11. And then C is 1/3 of that, so it'll be 2/11. And so there's our answer. And if you ever need to double check, right, we know that those are the only 3 possible events, so they should sum to 1, right? And so 6 plus 3 plus 2 equals 11. And so when you get 11/11, which is just 1. Okay, nice. So there's the answer to that problem. Today we're going to be talking a lot about various properties of probability. There's a lot of theorems, and so I don't want this video to be super long, so we're not going to go over really the proofs. Maybe some intuitive ideas using like Venn diagrams, but I want to stress before we start going over the theorems that the proofs are very, very important in this section. It's not really a prerequisite to this thing because I said the prerequisites were only multivariable calculus and some understanding of sets. So we're not going to really take too long on the proofs, but they are really important. And if you want mastery over math stats, it's very, very important that you understand the theory behind it and understand what is going on with these proofs. So I encourage you to look them up on your own. Okay, the first theorem is we'll have A, an event, and then with A prime, its complement. So a lot of times I'll just read this A prime symbol as just A complement. It means essentially, if you don't know, this is going back to the set notation, it means everything that's not in A, right? So if our universe is the set of all natural numbers, and A was all even numbers, then A complement would be all odd numbers. Okay, so we have this as our basis, and then we know when we have a complement that the probability of A is equal to 1 minus the probability of A complement. So this is a really important fact, and you're going to be using this when it asks you to find the probability of an event, but let's say that probability is really, really difficult to find the answer to. So instead, it might be easier to find the probability of the complement, find the probability that it doesn't happen, right, and then take 1 minus that probability, and you can get your answer that way. This one, let's go over a quick sketch. We can talk about this proof and this theory as more of an intuitive sense. So because remember, A complement is everything not A in the universe, that means the union of them have to make up the sample space. Also, we can't have A and not A happening at the same time, right? So their intersection must be the empty set. Okay, but what does that tell us? That tells us they're mutually exclusive, right? When their intersection is the empty set, they're mutually exclusive. So we know here that the probability of A union A complement, since they're mutually exclusive, that means it's just equal to the probability of A plus the probability of A complement. That's what we talked about last video. It's equal to the sum. But remember, this is just the sample space, right? So this is the probability, we get that this is the probability of the sample space. So we can say that these are all equal. And the probability of the sample space, by definition, is 1. So there's our solution. And then that gives us, yeah, let's put the pieces together just for sake. We know that this is equal to 1. So moving things around, we get that the probability of A is equal to 1 minus the complement. 1 minus the probability of the complement. Okay. So there's that one. Let's go over to a next theory. This one is also somewhat intuitive. And so I don't think it necessarily warrants a whole proof. But so for some arbitrary event A, the probability of A is less than or equal to 1. And this is kind of makes sense, right? We know that the event A has to be contained within the sample space, and we know that the probability of the sample space is always equal to 1. So it doesn't make sense that the probability of something that's contained in the sample space would be greater than 1. I guess that's another theorem that we're going to go over. Anyways, this makes intuitive sense, right? We can't have the probability of an event being greater than 1, because then that would imply it has more than a 100% chance of happening, which doesn't make sense, right? So that's not possible. It has to be at most equal to 1. Okay. This next theorem you'll see quite often. You might have already seen it before. It's very popular. It's very common. So we have for 2 arbitrary events, we'll call it A and B. We're going to get the following. The probability of So this is like remember, set notation, you can think about this as like A or B. The probability that event A or B happens is equal to the sum of the individual ones minus the intersection. Now you might be thinking, well, didn't we already come up with a definition for the probability between the union between two events? We did, but that's only if they're mutually exclusive, right? Because if they're mutually exclusive, then this right here is equal to 0, the intersection. Okay. We're not going to do a proof for this. Don't have the time, but let's look at some Venn diagrams so we can make intuitive sense of this, right? So when it's saying the probability of A in our Venn diagram, this whole thing is A, right? And so when it asks for the probability of B, this whole thing is B. So what's really happening here is we have to be careful that we're not double counting the intersection right here. We're not double counting the intersection right here. Because if we just do the probability of A, we're getting all of A, which includes that intersection. If we do the probability of B, we get all of B, and it includes that intersection. So if you just add them two together, and the intersection is not 0, then you're double counting it, meaning we have to subtract it off from the theorem. And so here, another way to think about this, A, is we know we can partition it into two different sets. So we know that it's A intersect B, so that middle part of the Venn diagram, the overlap, or it's A but not the parts with B. Okay, so try to make sense of that. It's going to be very important that you're able to look at Venn diagrams and sort of rewrite different sets. It's a big key to probability. Okay, the next theorem is a natural extension of that, and this one I'm going to leave to you guys to do the Venn diagrams for. This is if we have 3 events, so we have A, B, C, R events. And then we're going to get the probability of A union B union C is equal to the probability of A plus the probability of B plus the probability of C minus the probability of A intersect B minus the probability of A intersect C. I'm going to run out of room, so let me scoot it this way. Minus the probability of B intersect C, and then plus the probability of A intersect B intersect C. So again, I encourage you guys to draw the Venn diagram. You're going to have 3 events now this time, so it'll be a 3-sided Venn diagram. But to convince yourself that this is true, do that and see why are we subtracting off these things and why would we have to add this again. See what happens when you get it. And this here right here, this idea really comes from a combinatoric concept of inclusion-exclusion, which is actually really fun because you can extend this idea to, well, what if you have 4 things or 5 different things, right? How does that manifest? So that's pretty fun. Okay, next we have another theorem. If A is contained within B, then the probability of A is less than or equal to the probability of B. No proof. Let's look at what this means. If it's entirely contained, that means in our sort of intuitive sense, if this is B, A finds itself completely trapped within A. And yeah, this makes sort of sense, right? If A is smaller, if it's contained of things within B, then its probability must also be smaller. Okay. We've been over a lot of theorems, so let's try an example. This will be example number 1. We're going to get the probability of A is equal to the probability of B, and these are both 1/5. And we're also going to take the fact that the probability of A intersect B is equal to 1 over 10. Okay, and I want us to find the probability of B complement, the probability of B intersect A complement, and the probability of A complement intersect B complement. Okay, so let's first start with B complement. We're going to use the theorem that we talked about, the rule of complements. So we have that the probability of B complement, remember it's the opposite of B, so it's 1 minus, you take everything in the universe, the sample space, 1, and subtract. You can kind of think about this one as like B complement complement, right? But B complement complement is not B complement, which is just regular B. So this has got to be 1 minus 1 over 5, which is equal to 4 over 5. Cool. Next, probability of B intersect A complement. I think with these ones, B complement was simple because we just had to do the 1 minus thing. But for these ones, what does this mean, right? Let's get a picture going to see if we can get a better interpretation. So I always like to do Venn diagrams. We have two events, A and B. And this is saying B and also not A. So we want anything in B should be good, but we need it to also not be A. So it's going to be this region right here. Everything in B but not the intersection. So, well, this tells us, right, if we want B intersect not A, this should be, what, probability of all of B, and if we take the probability of all of B, that takes what we want, but it also includes the intersection right there, so we need to subtract off the probability of A intersect B. Okay? And so this would just going to be 1 over 5 minus 1 over 10, and so the answer is 1 over 10. Last part, we have that the probability of A complement union with B complement, and we want to find what this is equal to. So again, let's start by doing a Venn diagram. And when I draw this little box around it, that usually represents the whole universe, the sample space. So it includes things that are not within event A or B, because event A or B aren't necessarily our only outcomes, especially in this case because they're only equal to 1/5 probability. So it doesn't seem likely that those are the only two events that we're going to have, only two possible outcomes. So if this is saying not A, well, not A is everything outside of this circle, right? Outside of the A circle. But then it's also saying not B. So that's everything outside of the B circle. So really the only thing we don't want to include, that's a poor drawing, the only thing we don't want to include is this. We don't want to get this middle intersection right here. That's the only part we don't like. So what that means is we're going to start with the sample space, and our answer should just follow by subtracting off the middle, right? So this tells us the probability of A union the probability of B, sorry, A complement union probability of B complement should be equal to 1, the whole sample space, minus the probability of that little intersection right there. So this is 1 minus 1 over 10, which is equal to 9 over 10. Okay? So Venn diagrams are very important. They're your friends. And this gets into another discussion. This might be a review, so feel free to skip this if you already know about it. But we have De Morgan's laws. You might have talked about these when you're discussing sets. I'll just go over these and maybe try drawing Venn diagrams on your own to get a sense of why this works. But if we have the set A union B, and we take the complement of it, then it tells us we can distribute the complement as long as we flip the union to an intersection. That's the way I like to remember it. So these are still both complements. And the same thing applies in the reverse. So if you have A intersect B complement, then we can distribute that complement sign as long as we flip it. Okay? And these will help you when solving and approaching some of these problems. Pen went flying, unfortunately. Okay, let's keep going. So we have two final theorems to go over, and these are also very important. Like I said before, the proof to these ones, these are a little bit more complicated, so the proof to these ones are going to be, I believe, imperative to really fully understanding what's going on here behind the scenes. So I really encourage you to look them up on your own time. So for the first one, we have Boole's inequality. You might recognize the name Boole. He's a very famous, it's a very famous name in probability and statistics. So this says, for events, we have a sequence of events. So for events A1, A2, A3, we can have an infinite number. We know that the probability of the union of all events is an inequality, so we say it's less than or equal to the sum of all probabilities. And this sort of talks about plays into what we were talking about when you're counting up individual probabilities, there's going to be overlap. So when we sum these two together, we're summing the probability of A1 and then the probability of A2. But what about those cases where we have the probability of A1 and A2? So we're really double counting. Whereas with the union, this is just saying, when you think about in terms of set notation, this is just saying, the sort of where each of these individual events lie, and we're not including any sort of overlap that we might see. We're only counting the overlap once. And so there's a chance that this sum, there's a good chance, depending on how many events you have, that this sum right here is even greater than 1. And how does that make sense? Well, we know that individual probabilities can't be more than 1, but if we take probabilities and you take enough of them, then it could be that the case that they are more than 1. Okay, the last theorem, similar to this one, is Bonferroni's. It's Bonferroni's inequality. It's another inequality. So it's a similar thing, but now it must be a finite collection of events. So for A1, A2, and then we have to stop at some AK. If these are events, that's important. Then we know that the probability of the intersection of these finite events is greater than or equal to 1 minus the sum of these events. Sorry, the sum of the probability of the events. Okay? And so this plays into the rule of complements that we had. And again, I encourage you all to look up the proof. Okay, lastly, here's today's practice problem. So it's kind of more of a logic-based thing. You could do a formal proof if you are familiar with mathematical reasoning, or however you best want to show that the following is true. Whatever makes sense and whatever gives you a clear, intuitive picture that makes this statement true, do it however you like. So maybe that's drawing Venn diagrams, but your goal is to just show that the case is true, and it could just be a sketch. All right, that's all I have for today. Tomorrow we're going to be continuing more into probability, and we'll go over the solution to this problem. It's going to be, I think we're talking about conditional probability, which is a fun topic. So look forward to seeing you guys then.